A treatise on the motive powers which produce the circulation of the blood by Emma Willard, 1846. Chapter 1. The Theory of a Motive Power by Respiration, Animal Heat and Expansion. As written by the author, December 1839. This and the following sections contain the theory of a motive power by expansion, as made out by the author, December 1839, and circulated in manuscript, it being the same statement which was sent to Doctors Edwards in Paris, and the same which is alluded to in the letters of Dr. Marcy and others. See Appendix number 1. Several copies of it are now extant in manuscript in this country, and some in Scotland and in France. Additional remarks or explanations will be introduced in brackets or in notes. The oxygen returned in combination with the carbon in expiration is found to be the same in amount as that inspired in combination with nitrogen, i.e. in the atmospheric air, and on no law of chemical affinity can the conclusion be avoided that there have been chemical decompositions and recompositions by which caloric must have been evolved. The lungs are at least as much heated as any part of the body, and if oxygen and carbon would chemically combine anywhere in the system, they would here, and facts show that they do. We quote the following passages from Lieberg's Animal Chemistry, a work with which we do not, however, always agree. In contradistinction to this phenomena of vitality in plants, we know that the animal system absorbs oxygen from the atmosphere, and that this oxygen is again given out in combination with carbon or hydrogen. We know that in the formation of carbonic acid and water, the heat necessary to sustain the constant temperature of the body is produced, and that a process of oxidation is the only source of animal heat. The statements of other writers make the quantity of blood at the lungs of the whole, which they reckon at 35 pounds instead of 25. Both the quality and proportion vary in different subjects. So also do the dimensions of the aorta. Where the aorta is an inch in diameter, I believe there are more than 5 pounds of blood in the lungs, probably 7 or 8. We must not, however, lose sight of that law of caloric which regards its radiation in all possible directions, by which it is transmitted to adjoining substances till they are in equilibrio. Section 1. Expansion and motive power. The object of the following sections is to show that respiration operating by animal heat produces an expansive power at the lungs and thus becomes the principal efficient cause of the blood circulation. 1. The blood receives caloric at the lungs. A chemical combination of oxygen and nitrogen is inspired. A part of the oxygen is detained, and in its place carbonic acid gas and watery vapor are expired. Hence the caloric must have been evolved, and from its nature have passed the thin separating membrane and infused itself through the blood in the lungs. This we regard as already demonstrated, i.e. by chemical writers, as well as by the plain chemical phenomena, and the fact known to all, unlearned as well as learned, that the heat of the body originates at the vitals and is lost at the surface. 2. The blood must therefore expand. The expansion of fluids by caloric is a doctrine so perfectly understood and established that it needs no comment. But it is important to our purpose to consider that in this case there must be a very considerable expansion. Notwithstanding the great quantity of caloric carried off at the surface, enough is received to keep up a mean temperature of 98 degrees Fahrenheit. The temperature of venous blood is stated by Magendie to vary from 101 degrees to 75 degrees. That of arterial blood to be nearly 104 degrees, taking 88 degrees as the mean temperature of venous blood. We have difference of 16 degrees, which the vital action at the lungs upon the air there received is to supply. Later reflection has shown me that the whole difference between the extreme heat at the vitals and the coolness at the extremities is available in carrying on the circulation. See Appendix number 2. And the consideration that the force works in vacuo is highly important in showing its efficiency. In air, 212 degrees is the point at which a fluid boils, 72 degrees the point at which it boils in vacuum, which is 6 degrees below mean temperature, 32 degrees below that of arterial blood. The quantity of blood in the lungs has been stated by physiologists at 1/5 of the whole 5 pounds out of 25. This receives caloric, not like water in a vessel over a fire at one small surface only, but over a space which has been variously estimated, but by all acknowledged to be great. Making a computation on Dr. Keel's statement, the blood at the lungs receives caloric over a surface equal to the area of a circle whose diameter is nearly 17 feet, so that if the portion received at each particular point should be small, the aggregate must be considerable. 3. If the blood expands, it must move. This is perfectly evident, for to expand is to spring into a larger bulk, and the space which has contained the blood can contain it no longer, so that this expansion must be a motive power. 4. If the blood moves from the lungs, it must move towards the left ventricle of the heart, and from thence into the aorta, and so on through the arteries. For it must of the two directions take that in which it can move, and not that which it cannot. Here arise important considerations respecting the animal structure as a machine made for receiving streams of a fluid moved by the same agent which warms it, for it is not a power, like impulse, indifferent to direction. It is antagonist principle to gravitation, and its natural tendency is upwards. When particles of fluid become more heated than others with which they are connected, the heavier fall downwards and falls upwards the lighter. This, in the consideration of the whole subject, must be regarded as well as the absolute power produced by expansion, a power which, in its high and explosive state, is the most tremendously destructive of any known to man. Yet, as in the present case, where a fluid passes merely from warm to warmer, it is the most kindly and gentle force that can be imagined. Yet, if we consider that it is generated in the lungs over a space equal to a circle whose area is about 17 feet diameter, and concentrated in the tube, the aorta, of 1 inch diameter, we shall no longer be astonished at the force of the current found there. Suppose one should, on a mild spring day, place a lens on the diameter of 17 feet so that it would receive the rays of the sun, its focus being in a diameter 1 inch, would not its force be intense? Or suppose a case in which the laws of hydraulics are regarded, and which will on that point be more directly in point, a machine constructed like a syringe, with a piston of 5 yards in diameter, and a spout of 1 inch bore. How very slight must be the movement of such a piston to send a fluid from the spout with the velocity of the blood in the aorta